In episode 49, titled Load Balancing Methods, Round Robin, Least Connections, Weighted, Load-Based, the focus is on the rules a load balancer uses to decide which target receives the next request. When the exam asks about these methods, it is rarely asking for memorized definitions alone, because the tested skill is matching a method to workload behavior. A method that works perfectly for short, stateless web requests can behave poorly for long-lived sessions or uneven target capacity. The load balancer is making a choice every time, and your job is to understand what information it uses to make that choice and what assumptions that implies. These methods also interact with health checks and session persistence, but the core distinction is decision logic, not basic availability. If you can describe what each method optimizes for and where it breaks, you can answer most load balancing method questions confidently. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Round Robin is the simplest method, and it cycles through targets evenly without load awareness. In a pure round-robin approach, each new request goes to the next target in a fixed sequence, creating a roughly equal distribution over time. This simplicity is a strength because it is predictable, easy to reason about, and requires no real-time measurement of back-end conditions beyond basic health. It assumes that targets are similar enough that equal distribution is fair and effective, and it assumes that request cost is not wildly variable. When those assumptions hold, Round Robin provides good baseline distribution and avoids the complexity of metric-driven decision-making. On the exam, Round Robin is often associated with homogeneous pools and stateless workloads, where you want fairness and simplicity rather than deep optimization. The key is that Round Robin does not ask which target is busy, it only asks which target is next, which can be either perfectly adequate or dangerously naive depending on the workload. Least connections is a method that favors targets with fewer active sessions, attempting to send new work to the target that appears least busy. The decision logic assumes that active connection count is a useful proxy for load, which is often true when requests are similar in cost and connection duration. Least connections can outperform Round Robin when some targets are temporarily busier than others, or when requests are unevenly distributed in time, because it tries to avoid piling new work onto an already busy target. It can also be useful when session persistence is in play, because some clients may be sticky to certain targets, and least connections can compensate by steering new non-sticky sessions elsewhere. The method still relies on what the balancer can observe, and connection count is an observable metric even when application-level performance data is not available. For exam reasoning, least connections is often a good fit when request durations vary moderately and you want a simple form of load awareness. The nuance is that connection count can be misleading when connections represent different amounts of real work. Weighted methods introduce intentional bias so that traffic is directed toward higher capacity targets more often than toward lower capacity targets. Weighting is essentially an expression of relative capacity, where a target with a higher weight receives a larger share of requests over time. This is valuable when pools are not homogeneous, such as when some targets are larger instance types, have faster storage, or are dedicated nodes with better performance characteristics. Weighted methods can be applied to Round Robin, where the sequence includes targets multiple times according to weight, or to other selection algorithms that incorporate weights into the decision. The strength of weighting is that it makes distribution align with capacity rather than with simple equality, which can reduce overload risk for smaller targets. It is also useful during migrations and rollouts, where you want to gradually shift more traffic to new targets without removing old ones immediately. On the exam, weighting is often the safe answer when the scenario explicitly states mixed target sizes or uneven capability. The key idea is that weighted methods make the balancer intentionally unfair in a way that better matches reality. Load-based methods go a step further by using measured performance or resource metrics like central processing unit utilization or response time to decide where to send traffic. Instead of assuming that connection count or equal rotation reflects load, a load-based method tries to use real indicators of how stressed a target is. This can lead to better performance under highly variable workloads, especially when request cost differs widely across users or endpoints. Response time-based decisions can help route away from a target that is slow, even if it has few connections, while central processing unit-based decisions can detect targets that are saturated, even if connection counts appear normal. The complexity is that metrics must be collected, transported, and interpreted, which introduces delay and can reduce stability if the decision logic reacts too aggressively. Load-based methods can also be misled by metrics that reflect past conditions more than current conditions, or by metrics that vary for reasons unrelated to capacity, such as transient garbage collection pauses. For exam questions, load-based methods often appear as the most intelligent option, but the correct choice still depends on whether the environment can provide reliable, timely metrics and whether stability is maintained. The method is only as good as the measurement and feedback loop behind it. Choosing a method should be driven by how stateful the workload is and how variable the targets and requests are. Stateless workloads, where any target can handle any request without relying on stored session data, tend to tolerate simple methods because the cost of an imperfect decision is limited and failures can be retried easily. Stateful workloads, where sessions or long-lived connections matter, can behave poorly if requests bounce unpredictably between targets, and they may require persistence or careful distribution that respects session behavior. Target variability is another driver, because if targets are identical, fairness methods like round-robin are often sufficient. But if targets differ in capacity, weighting becomes a way to prevent smaller targets from being overwhelmed. Request variability matters, because if some requests are lightweight and others are heavy, methods that account for actual load can improve performance, but only if their measurements are stable. The exam often frames this as which method is best for this workload, and you should map statefulness and variability first, then select the method that best aligns with those characteristics. The correct answer is the one that fits the workload's realities, not the one that sounds most advanced. Consider a scenario with identical servers where round-robin fits naturally because the pool is homogeneous and the requests are relatively uniform. If you have a web tier composed of the same instance type, with the same configuration and the same expected request mix, round-robin provides a simple and effective distribution. Health checks ensure that any unhealthy target is removed, and round-robin continues cycling through the remaining healthy targets. The predictability makes troubleshooting easier because traffic patterns are easy to anticipate and changes in performance are more likely to reflect application behavior rather than balancing logic. This scenario also highlights why round-robin is often the default in managed load balancing services when no special requirements are specified. The exam often uses this kind of scenario to test whether you recognize that simple can be correct when conditions are stable. When everything is equal distribution is usually a reasonable choice. Now consider a scenario with mixed target sizes, where weighted distribution is safer because capacity is not uniform. Imagine a pool where some targets are larger and can handle more concurrent load, while others are smaller and intended to carry less traffic. If you use round robin, the smaller targets receive the same number of requests as the larger targets, increasing the chance they become saturated and slow down the overall service. Weighted methods allow you to steer more traffic to the higher capacity targets, reducing overload risk while still keeping lower capacity targets in service. This is also useful when scaling up gradually, where new, larger targets are introduced and you want to shift traffic toward them without abruptly removing older targets. The exam often signals this scenario with phrases like different instance sizes or uneven capacity, and weighting is usually the intended answer. The key is that fairness is not the same as effectiveness when the pool is not equal. Least connections has a pitfall that becomes obvious when sessions are long-lived, because connection count stops reflecting real capacity in a meaningful way. If some clients hold connections open for long periods, such as with streaming, remote desktops, or persistent application protocols, a target can accumulate many long-lived connections that consume relatively little central processing unit. Least connections would then avoid that target, even though it might have plenty of capacity for new short requests, while other targets with fewer but heavier connections might be more stressed. The method also fails when connection duration varies widely, because a target with fewer connections might still be the slowest if those connections are expensive. In these cases, least connections becomes a misleading proxy, and it can cause uneven performance or unfair distribution that does not match actual load. The exam tests this by describing long-lived sessions and asking which method might perform poorly, and least connections is often the correct pitfall choice. Recognizing when the proxy breaks is part of selecting methods responsibly. Load-based methods have their own pitfall, and it often shows up as unstable traffic oscillations caused by metric lag and overly reactive steering. Metric lag means the data used to make decisions reflects the past, not the present, because metrics take time to collect, aggregate, and deliver to the balancing logic. If the balancer reacts quickly to a spike in central processing unit or response time by shifting traffic away, it may overload other targets, causing their metrics to spike, which triggers another shift, and so on. This can create a feedback loop where traffic sloshes between targets in waves, reducing overall stability and sometimes worsening performance compared to simpler methods. Oscillation is especially likely when the pool is small, the workload is bursty, and the control logic is not damped with smoothing or thresholds. The exam may describe a system where traffic patterns become erratic after enabling load-based steering, and the underlying cause is often metric delay and overcorrection. The lesson is that measured steering requires a stable control loop, not just more data. A method that uses metrics can be powerful, but it must be tuned to avoid chasing noise. A practical quick win is to pin sessions only when truly required, because unnecessary persistence can reduce the effectiveness of almost any distribution method. Session pinning can be helpful when the application stores state locally and cannot serve a user consistently across backends, but it also creates uneven distribution and can leave some targets overloaded while others are underused. If you can externalize session state or redesign the application to be stateless at the tier behind the balancer, you reduce the need for pinning and allow distribution methods to work more effectively. Even when persistence is required, it should be applied thoughtfully, such as limiting its scope to the minimal set of paths or workflows that truly need it. This reduces the chance that the balancer becomes constrained by sticky behavior that it cannot correct. The exam often tests this indirectly by describing authentication issues or uneven load and expecting you to recognize that persistence is a trade-off. Pinning is a tool, not a default, and using it only when necessary is an operational discipline that improves both performance and resilience. A useful memory anchor is even, least, weighted, measured, choose wisely, because it captures the progression from simple fairness to proxy-based load awareness to capacity-biased distribution to metric-driven decisions. Even corresponds to round-robin and similar fairness-based methods that assume homogeneity. Least corresponds to least connections and similar proxies that assume connection count reflects load. Weighted corresponds to intentionally biased distribution that aligns traffic share with known capacity differences. Measured corresponds to load-based steering that relies on metrics like central processing unit or response time to reflect current stress. Choose wisely is the reminder that no method is universally best, and the correct choice depends on statefulness, request variability, and target variability. This anchor also helps you spot exam traps where an advanced method is offered as an answer even though the environment cannot support reliable measurement or the workload would be destabilized by reactive steering. When you can explain the anchor, you can justify method choices with clear reasoning. To apply the concepts under exam pressure, you might be asked to pick a method and justify it based on constraints such as mixed capacity, session behavior, and workload variability. If the pool is identical and the workload is mostly uniform and stateless, round-robin is often appropriate because it provides simple, stable distribution. If targets differ in capacity, weighting becomes important to avoid saturating smaller targets and to align traffic with capability. If connection count is a good proxy because sessions are short and similar, least connections can help balance transient imbalances more effectively than pure rotation. If workload cost varies widely and reliable, timely metrics are available, load-based steering can improve responsiveness, but it must be configured to avoid oscillation. The exam expects you to connect the method's decision logic to what is true about the workload, not to make a choice based on popularity. A correct justification explains why the method's assumptions match the scenario's constraints and why alternatives would likely fail. To close episode 49, titled Load Balancing Methods, Round Robin, Least Connections, Weighted, Load-Based, remember that these methods are simply different rules for selecting the next target, each with strengths and failure modes. Round-robin cycles evenly without load awareness and works well for homogeneous pools and uniform requests. Least connections favors targets with fewer active sessions and can help when connection count reflects real load, but it can fail with long-lived sessions or uneven request cost. Weighted methods bias traffic toward higher capacity targets and are safer when pools contain mixed sizes or when gradual traffic shifting is needed. Load-based methods use metrics like central processing unit and response time, offering better alignment with real stress at the cost of complexity and the risk of oscillation when metrics lag. Your rehearsal assignment is a comparison drill where you describe the same workload under each method and predict how traffic would distribute and where it could break, because that mental simulation is the simplest way to master method selection the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.